This example is not in your notes, but I want us to take a minute to look at these histograms so that we can understand how to describe a histogram. So this data is created using 67,810 hourly elevation levels for Lake Murray, which is a man-made reservoir in South Carolina. It's used mostly for recreation, boating, fishing, water sports, things like that. But it also is used to provide backup hydroelectric power for South Carolina electric and gas. So the lake levels are fluctuating with the highest levels in the summer so that you have safe boating and good fishing conditions. And then the lowest levels are in the winter, and that allows for preserving the water quality. Water can be released at the dam in case of heavy rains or if they need to let out water to maintain winter levels. So that's a little background of where this data is coming from. But what we want to understand is that this histogram is looking at these hourly heights or hourly depths, and it's from 2007 to 2015. Whether we use the count or the percent, we get the same looking histogram. So that's an important thing to recognize, is that the histogram will look the same whether you have the counts or the percent that represents of the total data set. The percents are calculated by taking the counts and dividing by the total number of observations that there are. So you get the same image, but notice that the scale on that vertical axis is different. We see that most of the values are there around 357 to 358. So the center value would be around 358. The shape of this is single peaked because you have that one major peak, but it is left skewed. So notice that there are a few very small elevation levels. There's some 350, 352, 353, but most of the data is there on the right. So this is skewed to the left. The tail, if you were to imagine this was an animal, the tail is there on the left. So what does this mean? Well, if you had someone who was fishing and they wanted to see how often the lake reaches a certain level, then the fisherman would know that this lake is going to be 358 or higher about 35 to 40% of the time. It's very rarely as low as 350 or 352. So our center around 358, the shape single peaked and skewed to the left, and then the variability, most of the values are there between say 355 and 359. Another application of histograms is you can actually look at patterns for authors. So you can look at someone like William Shakespeare, and you can see that most of the words that he used in his writing were actually pretty short words, 3 or 4 numbers. But there are 3 or 4 letters. There were a few times that he used much longer words, but most of the words are actually pretty small. We can look at histograms, but another type of display that can be very useful, particularly for small data sets, is what's called a stem plot. So a stem plot is going to show you the exact same thing as a histogram. It's going to show you the shape, the variability, and the center. But what it's going to be nice is that you're actually going to use the raw data. So the stem plot, you can actually see what the actual values were instead of just knowing that they fell in a particular range. So the way you create a stem plot is that you separate each observation into a stem, and the stem would be all the digits except the very rightmost. So whatever that rightmost digit is, that's the one that's going to be the leaf. Everything else will form the stem. Stems can have as many digits as you need, but you do want to make sure that all of your numbers go to that same digit or place value. Don't worry and don't include any commas or decimal points with your leaves. So the leaves should just be 1 unit at the end. Then your stems are going to be in a vertical column with the smallest value at the top, and you'll draw a vertical line to the right of that column. And then starting at that smallest stem, you'll increase by 1. Even if there's nothing in a particular section, you still have to write it so that you have them all evenly spread out. And then once you have all of those stems, then you're going to write the leaves on each row to the right of the stem. You also need to make sure that they're in increasing order from that stem. So looking one more time at the data from the percentage of adults 65 and older for the different states, we see that the values range from 7 to here we can see it's 17.3. So we start with a stem of 7, and then 8, 9, 10, and count by 1 until we hit 17. Then the leaf, that first one, represents 7.7%, and we know that here because of the key. We have a 9.0, a 10.9, a 10.7, a 10.3, and so on. But I want you to imagine that we turned this graph perpendicularly, so a 90-degree shift, and you can see that these numbers are actually representing the same heights that the histogram was showing. So a stem and leaf plot is really showing the same thing as a histogram, but instead of drawing bars, you're actually demonstrating what the actual data values were.